Welcome to the glass plate. In the coming exercises, we're going to take a look and revisit the problem that we did in exercise 2.1, where we looked at making hot water for a cup of tea. And we did that in a very simple way, and we're going to repeat that here. And then we're going in the next examples, make it more realistic. We had an electric cooker that produces heat, and that heat flows into our water. And we assume that everything that is produced here ends up as heat flowing into the water. We have an initial temperature of the water, T0, and we're going to use 20 degrees Celsius. And we have a given volume, say half a liter. And we want this, in this exercise, to bring from 20 degrees C to 80 degrees C. And we wonder, how long does this take? Okay, first we'll do it just in a very simple way without really using the concept of balances, although the balance concept is behind our reasoning. We could say that if you have to heat it up to 80 degrees, then there is a certain amount of thermal energy that you have to give to the system, and that is the mass, the specific heat that multiplied by the temperature change that you want to have. And we have at our disposal a cooker that has a kilowatt of thermal energy to deliver, so a power of P, and if you put every second this amount of energy, this amount of joules in your system, this is the temperature rise. So the energy put in is the power times time, basically how long you leave the apparatus on. And obviously, since we know this P, we know this side, you can back out that it takes 120 seconds in this example to heat from 20 to 80 degrees. Fair enough. This is easy, quick and dirty, works fine. We can do that in the format of a balance. We have seen that before. It's an unsteady system. So you write the standard form. There is no internal production. Heat is flowing in, phi q. There is nothing flowing out in this example. We ignore losses to the surrounding. We ignore vapor production. And here we need to write the energy in terms of temperature, and that is rho v Cp T minus a reference temperature. Basically, you say here, okay, I start from my 20 degrees or something like that. If I heat up, this is the amount of energy that I need to put in, just like what I wrote here, but now in terms of density and volume. This we have done before, is a not too difficult differential equation. We need to integrate once, so we need one boundary condition, initial condition, and that is listed here. At time t equals 0, I have given temperature. So this gives me, for the temperature change over time, phi q over rho v Cp. During the differentiation, this reference temperature drops out, but when you integrate back, you get back an integration constant, and that is T0 via the boundary condition. And obviously, if you compute how long it takes before you reach 80 degrees starting from your 20, you'll get the same answer. What we will change is what happens here. This is the coarse way of dealing with it. There's only inflow. There are no losses. In practice, there will be losses. In the next glass plate example, we'll take a look at how you could model these losses and what they do to the temperature and to the time, as well as to the temperature increase in time.